Good morning. It's a pleasure to be here, and I want to thank the organizers for the opportunity to present. This morning I'll tell you about two experiments, or one experiment and one to-be experiment, where the crux of the experimental method is to, as precisely as possible, estimate phase. And so I want to start with a cartoon simulation, just to remind us that what some of the limits for phase estimation are in the quantum sensing situations that are relevant to the work I'll describe. So the horizontal axis is the phase, and the vertical axis is the number of atoms, in particular, detected in an excited state at the output of an interferometric sensor. And it's well known that if for a given number of atoms that the ability to resolve the phase is given by the Poissonian statistics associated with wave function collapse, also known as shot noise. So for example, if we are sitting on the side of a fringe and want to determine the phase of this interference fringe, we're limited fundamentally by, if the particles are uncorrelated, by shot noise. And so by counting the number of particles, we see that due to the randomness of the wave function collapse, we have a width of that distribution, which fundamentally, via the slope of this fringe, impacts our ability to precisely determine phase. So the question is, how can we do as well as possible in determining the phase of this fringe, or the phase output of this interferometric sensor? And the relevance is that that phase is correlated with something that we want to measure. For example, it could be a clock, or the example I'll use at the end of the talk is the example of electron microscopy, the phase-sensitive electron microscopy. It's also well known that by exploiting many-body entanglement, that one can defeat the shot noise limit. And so here I'm showing you some recent 2016 data from my group, where we did a kind of an atomic clock prototype experiment with an atomic rubidium. And so I'm going to show you the probability distributions if you sit on the side of a fringe and count the number of atoms at an output port. And the way these experiments work is you prepare a number of atoms in the ground state, you then excite to an excited state with a probability. Then if you do not entangle the states, you wait, and then you follow with another excitation pulse, a so-called Ramsey sequence, and then you measure the number of atoms in the excited state. And the phase of the interference fringe that you observe after that sequence helps you build a clock. And so if we do not correlate atoms, here I plot the number of fluctuations reference to the midpoint on the Bloch sphere and the probability of that occurrence, you are simply limited by atomic shot noise. And that's this blue histogram, and this was an experiment done with close to 1 million atoms. And clearly the width of this histogram determines your ability to, limits your ability to make a phase inference. Now, if you use a procedure, which I'll describe in a moment, to correlate atoms in that ensemble in a many-body way or a many-atom way, you can introduce correlations that collapse the width of that histogram. And so, for example, this orange histogram is the result of following one of these entanglement procedures, where the fluctuations in the atom number across the ensemble has been reduced, or we call it squeezed, by 20 dB, or according to that jargon, the width of this distribution is 10 times narrower than the width of that distribution. Clearly, this has substantial impact in your ability to build an atomic sensor, because the narrowness of this distribution is directly proportional to the noise performance of in this case, the clock, the sensor. This yellow distribution is one where a phase shift has been applied, and this just shows you that the narrowness of this distribution can be used to infer a small phase shift. All right, so how do you realize this type of situation? Well, first, it's important to note that there are lots of experimental protocols that will allow you to collapse the variance of a shot noise distribution. But there are not a lot of protocols that will allow you to maintain the coherence of the system that's required for an interferometric sensor. So whatever protocol you use, it's vital that you retain coherence as much as possible within the limits of the back action of the measurement. And so this is experimental data demonstrating that for what I showed you on the previous slide, that the coherence is maintained to a high degree. So this is the phase of the fringe. And this is according to the following sequence, where atoms are prepared in the ground state. They're excited with a microwave pulse to a superposition state. Then there is a correlating probe pulse or an entangling pulse, which I'll describe on the next slide. And then finally, there's an analysis pulse, which is meant to show that the microwave coherence, which has been initially established by that first pi/2 pulse, persists after the squeezing event that reduces the variance of the distribution. And that's crucial. If I squeeze the distribution or do something to the distribution to narrow the counting statistics, but then I still do not have a phase coherence, I no longer have a sensor. So in some sense, this protocol has to be non-destructive of the coherence. So what's our strategy? Well, the strategy is to follow a well-hewn path to essentially count the number of atoms in a given state using non-demolition measurements by essentially measuring the phase shift associated with an individual atom as it's associated with the propagation of light through the atoms in the cavity. And this represents itself as a shift in the resonance frequency of the cavity when the cavity is probed by quasi or nearly resonant light. So here's the level diagram. And so here are the two states of metrological relevance. And then there's also a third optically excited state that's used to do the non-destructive probing. And just to kind of give you a feeling for how this works, atoms are somehow manipulated to be in the waist of this probe laser, 780 nanometers, which is tuned midway between the hyperfine transition in atomic rubidium. And by sweeping the frequency of this laser, one can essentially count, as it resonates with this high finesse cavity, one can essentially count the number of atoms in a given state by looking at, for example, the phase shift of the light that's transmitted through the cavity. Crucial to the results I just showed is that the atoms are also confined in a well-registered 1560 nanometer laser, as I'll show on the next slide. The idea here is that the 780 nanometer laser is there to measure the index of refraction of individual or collection of atoms. And you want to make sure that measurement happens with uniform coupling across the ensemble. And to enforce that coupling, it's useful to have a confining potential for the rubidium atoms, as shown in black, where the rubidium atoms happen to be well registered with respect to the antinode positions of the probing light. And this property is going to be central to some more recent results I'll show you in a few slides. And in terms of obtaining the 20 dB variance reduction, it was very useful to have that uniform coupling across the array. So just in terms of some experimental details, this is the apparatus. Here's a source of cold atoms, a quote 2D MOT. Here is a high finesse cavity for those who are experts in this area in the field. In the audience, these are the cavity parameters, 200,000 finesse, waist of about 110 microns, free spectral range of 1.3 gigahertz. The cavity line width is about 8 kilohertz. And the cooperativity for a single atom is approaching 1. The readout of the cavity resonance, which was done in Homodyne, and here's a schematic of the Homodyne readout, which resulted in this curve as, for example, the 780 nanometer laser is swept through the resonance. So the strategy to create the squeeze state is to load atoms into the cavity. In comes the 780 nanometer probe, and then to basically look at that homodyne signal and to determine the number of atoms in the cavity. And the crucial point is that determination can be done essentially non-destructively in such a way that it maintains the phase coherence associated with the clock transition. Just to drive this point home, that the atom is basically something that shifts the resonance frequency of the cavity. Here you can measure, well, this inset shows that for a cold cavity, this is early data, for a cavity without atoms, as I sweep the frequency of the 780 nanometer probe, there's one resonance frequency. If I put atoms into the cavity, then the resonance frequency shifts, and essentially measurement of that shift is the measurement of the number of atoms in the cavity. So with this non-destructive measurement and the preservation of phase coherence, one can implement an atomic clock measurement sequence, and that's shown here as illustrated in the Bloch sphere. A first pi/2 pulse puts atoms on the equator of the Bloch sphere. Then in comes a squeezing interaction that, due to back action, creates this ellipsoid. This is not quite to scale. For the actual experiment, the aspect ratio of that ellipsoid is about 1,000 to 1. Then here comes the Ramsey interrogation sequence. Pi/2 rotates that so that this is on the Bloch sphere what the atomic many-body state looks like. It processes in a standard way of an atomic clock, and then a final pi/2 pulse projects that precession on the z-axis, and you detect the number of atoms in the ground state or the excited state. And then from that population, you can infer the performance of the clock. And a common thing to do in the clock community is to measure the Allen variance associated with the clock. And so this is such a graph. This is the averaging time for the clock output in seconds, and this is the fractional frequency stability. In no way is this a record-setting clock, but it does show that using such squeeze states, one can improve clock performance. This is uncorrelated inputs, and then this is with the squeezing protocol. This data was limited in two ways. First, we had a somewhat less than state-of-the-art local oscillator for the microwaves that limited the phase noise performance of the clock, the squeezing, to 10.5 dB rather than closer to 20 dB that the squeeze state indicated we would have. And secondly, and probably crucially, the performance is limited by any clock wants interrogation time to have high performance. That's the time between the two Ramsey excitation pulses. And in this proof of concept experiment, that time was just 200 microseconds. We would like to stretch that time out to as long intervals as possible in order to improve the fractional frequency stability of the oscillator. So let me skip to this slide. Here's recent data that shows our attempts to do that. For the previous work, the squeeze state was interrogated in the lattice and then probed also in the optical lattice. And the defect with that scheme is when the atoms are in the confining optical lattice, is perturbing the coherence of the atomic oscillators, and it leads to a somewhat rapid deterioration of the phase coherence. So it's desirable to build a clock not to contain the atoms in the lattice, but to release them to free space where it's a more pristine environment for maintaining phase coherence. And so that's what we do here. We create the squeeze state in the cavity as shown previously, and then we release the atoms from the cavity, let them fall under the influence of gravity, and during this fall time, we now have the opportunity to do a Ramsey interrogation. We haven't quite got to that state yet of sophistication. What we've done is release the atoms from the cavity after squeezing them, let them fall for an interval of time that's shown here. This is, I'm sorry, the units are not there. This is a free fall time in milliseconds, so this is 10 milliseconds, and this is just after release. And we measure the number of atoms in the excited state with not the cavity, but resonant fluorescence probe. So we count the atoms in two ways. One, we count them by looking at the resonance frequency for the 780 nanometer light in the cavity. Then the atoms are released, and we count them a second way by looking at the resonance fluorescence. And then we can, by correlating the probe to the camera, we can assess whether the variance associated with the atom number fluctuation has been reduced with respect to shot noise. In this protocol, we also use a deterministic squeezing methodology, so the atoms are squeezed near the JZ equals 0 point on every shot. And we're quite excited that now we are able to extend this squeezing performance out to timescales that are now relevant for what we think are going to be pretty high performance microwave clocks. At 10, this system will now support up to 10, well, close to 10 millisecond interrogation times. The squeezing is not up at the 17 or even 10 dB level, but we're now sitting at 6 dBs, and this is before we include the effects of microwave oscillator phase noise, and we're still trying to chase down what's undoubtedly some technical noise associated with a mismatch between the coupling of the atoms when they're squeezed, and here it's crucial that they're coupled at uniform cavity coupling at the antinodes in the cavity, and the coupling of which we detect them, which is the probability of a single atom resonantly fluorescing so many photons. So this is work in progress, and our hope is that in short order we'll be able to extend these interrogation times to higher performance clocks. I want to point out that crucial to the performance of this type of methodology is the fact that the atoms are correlated or entangled. And there are many ways of thinking or talking about or characterizing the entanglement. Often that's done in the context of entanglement depth. But in 2016, there was this paper that also described the methodology of how to think about the correlations in terms of bell pairs that coexisted in the squeeze ensemble. And so following this paper last year, we had basically looked at the level of bell correlations in this ensemble, which could be inferred from a witness that was constructed from basically the coherence and then the variance measurements, the collective coherence and variance measurements. So we're not doing individual bell measurements for each atom on the ensemble, but inferring bell state correlations from the collective observables. And this witness for a bell correlated sample, a quantum sample, when it drops below 0, indicates the presence of bell correlations. Okay, so that's an atom sensing application. In the last minutes, I want to quickly describe another application of phase estimation, and that's in a seemingly distant field of transmission electron microscopy. And there, a holy grail is to non-destructively image small biological matter. For example, here's a protein. These dots are individual atoms. And it would be nice to be able to image this without destroying it. In current electron microscopy protocols, cryo-EM, for example, electron probe goes in, and sure, you get a nice picture, but it absolutely, it basically obliterates the sample. It's much as in the previous discussion, if I could measure the number of atoms in the excited state, but I would completely lose a coherence. So that's kind of what's happening in electron microscopy. And it's an interesting question to ask, can we improve electron microscopy by using or exploiting quantum measurement techniques? That's to address a holy grail challenge for this field as can you image something living at the small scale? And there's a lot of, well, there's actually not much debate. I think the consensus in the field right now is that, especially cells, there's just kind of no way that you could take a non-destructive image of a cell with electron microscopy. And what I'd like to do is to kind of set forward a more modest challenge. Can you be somewhat non-destructive for nanometer scale proteins? So just to kind of set the stage for what the imaging target looks like, it looks like a phase shift to an electron beam. How big is that phase shift? Well, it's small, just like measuring the phase shift of an atom in a cavity was small. And so for a 300 kilovolt TEM, for example, the phase shift electron experiences when it sees the electric potential of this object is about 60 milliradians. And associated with that phase shift, there's also some inelastic loss. And it's difficult to quantify directly, so what we've done here is just characterize the inelastic loss of the electron probing through 20 nanometers of ice, which is the vitreous ice, which is usually the holder for this, this molecule is embedded in. So that sets the scale. We want to measure we want to measure a small phase shift with a coherent electron probe. And so what's the strategy? Well, one strategy is the following. Imagine this as being a pixel in the image plane of the electron microscope. Let's make the probe go through that pixel multiple times, much as in the cavity, the 780 nanometer light resonated through the atom ensemble many times to measure precisely the frequency shift of the cavity. In comes the electron beam, and maybe we can build a microscope where this is arranged so that the electron goes through the thing you want to image many times. Why is this good? Well, I'm measuring a small phase shift. If I can make that small phase shift larger, it's going to be easier to measure the phase and determine the presence of that biological matter. And so arranged for multiple passes, the detection noise, which is given here now by the read noise of the detection of the electron, is the same, but the signal is much larger, and so the signal and noise of this measurement improves somewhat dramatically with the number of passes through the sample. So this seems like a very simple classical measurement protocol, but there's I think, an inspiring paper from Seth Lloyd and collaborators in 2006 that was aimed at describing quantum metrology protocols. And in this paper, this is the abstract. I want to highlight in yellow one of the concluding sentences. They said, basically, to paraphrase, you can entangle the probe particles like we did in the first part of the talk and create a marvelous squeeze state, which is going to give you an enhancement in the phase readout of the system. Alternatively, a multi-round protocol, that is passing a single object through the ensemble multiple times, can also result in similar enhancement in precision. Doesn't involve entanglement. Now you say, well, okay, this must be cheating, and this is, you just described to me a simple protocol that is almost classical in nature. It can't be that you can describe this as a quantum phase estimation technique. And here I want to say that basically, when you're doing a metrology protocol, you have to ask, what is the resource you're trying to protect? And a clock, you need to make a measurement in a finite duration of time for technical reasons. The resource you protect against in a microscopy is damage. And so we're looking for protocols that minimize damage. What is the best state to use for microscopy that will minimize damage but also give high resolution phase output? And it turns out it just doesn't matter. I could take, if I have n electrons and I have my heart's desire entangle them up, I will not do better than taking those electrons and making them run through the sample n times if I don't care about how long the measurement takes, if I only care about damage. So with that simple idea, let's go and think about how the impact of this in terms of implementation. This is an animation due to Colin Ophis at the National Center for Electron Microscopy up at Berkeley. And what he's showing is an electron propagating through and passing through this biomolecule many times, and then every now and then you periodically outcouple it and take a picture. I'll show you the results of some simulations that he's done in just a moment. How does this work? Well, electron optics, you can create a resonator by lowering a potential and letting an electron wave packet in. This electron wave packet is time triggered and either by pulsing a gate electrode or using a laser triggered photocathode. And so you can let we call this lowering the barn door, you can gate the electron into the cavity, and this is a 1D view of a 3D situation. The electron bounces back and forth between these two potential barriers when this barrier is raised again after it's coupled in. And then n times later, or m passes later, I should say, the electron is coupled out to a detector. So that's the scheme. How well does it work? Well, here's some simulation. This is not data, this is simulation showing detection noise. It's kind of a state-of-the-art multi-slice simulation following the methodologies of the electron microscopy field. This is due to Kalanophis, again, up at Berkeley. And we're looking at two different samples. Here is something that's essentially DNA, and this is a more complicated biomolecule. Up here is a number of passes in the electron microscope, and here is the dose, the number of electrons that the image sees. And I have two more slides, Christoph. And you can see that as you increase the dose, the signal to noise and the readout, say for m=1 or m=16 passes, improves as you would expect. But it's crucial to compare, for example, a performance at 1 pass to performance at 16 passes. And what's interesting here is that the 16-pass image is taken with an effectively a much lower dose. This is accounting, this 8 electrons per angstrom squared is accounting for the fact that the electron has gone through the sample 16 times. And you see that the image quality is essentially the same, but for this image at much lower electron dose. Now, what's the relevance of 8 electrons per angstrom squared? Well, the known damage threshold for imaging DNA is between 10 and 20 electrons per angstrom squared. So here's a way of, I don't want to say non-destructively, but low damage imaging of DNA in a way that's just not possible right now. If you turn up the beam current to this dose, then what happens is the kind of DNA just melts in the image. And this down here shows data for a more complicated molecule. This slide basically is also from Colin. It shows that you can use state-of-the-art reconstruction techniques by changing the tilt angle of how you image the sample and then doing a reconstruction. You can get full 3D reconstructions of the small stuff in this case at almost low damage regime. So that's exciting, and we're anxious to go and see if this works. So right now in Czech Republic, an electron microscope of multi-pass TEM is being built. We've been designing this for more than a year, and these are the machine drawings, and metal is being cut now. Here's the gun. Here is the CAD schematic of the microscope column, and this is the electron optics associated with this. This is a tricky design because the electron has to maintain its spatial mode as it oscillates through the sample multiple times. And so a lot of thought has gone into, I know if you haven't been looking at this is maybe too much detail, but there's a mirror right there, and that mirror has to be aberration corrected and nearly perfectly performing. Concluding remark is that just some simple math, we can go and look at the damage performance of this protocol. And if you're familiar with dark field microscopy, the probability for a single probe going through the pixel of detecting, for example, an electron behind something that is giving you a dark field signal is proportional to the phase shift of the probe through that object. And so if I can go through phase shift squared, I should say, if I can go through the object m times, that signal becomes m squared times brighter. If I say I want to detect that object, I need to have the detection probability beyond the order of unity. That's my minimum threshold. So I need to send enough electrons through so that this product is equal to 1. And then when that's equal to 1, I can also kind of observe what the absorption limited damage would be. And the take-home point is that for the protocol I just showed you, the damage can be much less than 1 per pixel, which is exciting news. And in fact, if you can, it essentially shows that multipassing through the sample will reduce the damage, but it also shows that, this is my last slide, we can get into a counterfactual measurement regime where maybe the interrogation can be completely non-destructive. And for that, I just want to refer you to this simple argument where if I build a Mach-Zehnder interferometer and I put an object in the Mach-Zehnder, if it's initially aligned so that no counts come at detector 2, and then the object is placed in one of those arms, if I see a count at detector 2, I know that the object had to have been placed there. But because I saw the count in detector 2, I know the probe could not have interacted with the object. Same thing's happening in that multi-round protocol. If I detect the electron at the output, I know it couldn't have interacted with the object. And that opens the prospect of truly damage-free microscopy, which we hope we can realize. At that, I'd like to conclude and thank you for your attention. Thanks.
Thank you very much.